years of experience. He has administered several top 500 supercomputers, including Falcon, LMH, and Sawtooth. He has always had a passion for trying to minimize the barrier to entry for HPC, and to this end, he has implemented and set up the INL's HPC's open on-demand instances. And more recently, he has been exploiting containers and their viability in replacing bare metal installs and HPC systems. He graduated from University of Nevada, Reno, and is currently pursuing his PhD in computer science from the University of Idaho, focusing on the reinforcement learning schedulers. So his talk today will focus on software quality assurance for high-performance computing containers utilizing MVAPICH2 and the MOOS framework. So let's give a big welcome to
Thanks. I forgot about the tour, so I noticed everyone left. So I thought you were a little afraid this would be boring. So I'll try and make it a little more entertaining. Again, thank you for inviting me here to talk. I'm pretty excited to be here. I took some slides from last year as well, and we'll see those at the end and improve them a little bit, I think. So I'll make this a little more interactive, and sorry for the folks online. I can't see you raise hands to my questions. Who here has used containers? All right, a couple people. Don't be shy, it's okay. All right, now who here has used Docker only? Okay, one person, that's, I like the, oh, that was good. Okay, anyone in here a system administrator themselves? Or dabbling it on the side? All right, so I can make up anything. Oh, you're gonna fact check me, I don't like that. All right, so we came up with this strategy because it's a lot to maintain an application tree. So since a lot of you aren't system administrators, I take it most of you are users of HPC, yes? No one in here doesn't use HPC? Okay, so you get a lot of tickets. You get a lot of people coming in and saying, hey, I need this application, I need this application. I also needed to work with these different types of MPIs, version 231, 232, 235, 198, or whatever it is. And so these trees can get really complex. And so what we're trying to do with these containers here is come up with a way to handle these various different facets here. So verification and validation. Is my code going to run correctly in 5 years, 10 years? Is it going to be running the same between different systems? That's part of reproducibility as well. So what about portability across HPC systems? So let's say I built a container at INL, and we have several different systems there. Different architectures, Intel, AMD. Is my container going to produce the same results? What about if I give my container to someone else here, and they go run it at their institute? Is it going to be the same? And that's the kind of pieces we want. We want these types of reproducibility and portability. Now, the other piece is simplification. So I mentioned that we're going to use the MOOS framework. So who here has built the MOOS framework? Anyone? All right. We talked earlier. I like that. Is it complicated? Is it easy to build? They have good steps. They have decent documentation. But there's a lot of moving pieces to it. What about other complicated codes? Allegra, other big codes, I don't know, I'm drawing a blank. But there's lots of them out there that have lots of different dependencies. Wouldn't it be nice if the developers of those codes said, hey, here's this thing that you can run and it has all the dependencies in it for you. I even built it for you. But if you want to build it yourself, it's guaranteed to build in here. That's kind of what these environments are for. And then finally, if you've used an HPC system, now I put security here, but we got to talk about that. It's not security that I'm checking it with, I can't think of the one we use, Nessus at the lab, and saying like, hey, there's these vulnerabilities in this space. But when the system administrators were guilty of applying security patches, so when we patch the system, is your code still going to work afterwards? Is it going to work the same? These containers kind of insulate you from that, and that's what we're going to show. So a container creation. Since some of you have used containers and some haven't, a very simple way to think about this is if you've used Singularity or Docker or Aptainer or Podman, one of those things, you can do a Docker pull or a Singularity pull, for example, and it grabs something from the cloud and brings it down. And then you have these giant libraries of containers that you can use at that point. If I need a Redis server, I'm not going to install it. I'm going to pull down a Docker container for Redis, and I'm going to start that instead. This way I don't have to keep installing applications. I can just have this library of things for me to use. So what about if we decide to use our own definition file? A definition file is just a set of commands for pulling down a container and doing something to it. You always have to start with something. Now, We don't have to use container libraries from the cloud, for example. We don't have to use Singularity Hub or Docker Hub. We can actually just use a repo that we hosted in our own space and build a container from that. But the question becomes then, if I'm doing this kind of process over and over, is let's say that we built it today at, it's 4:40 right now here. Let's say we built it right now, and then I build it again tomorrow. Can anyone here tell me if it's exactly the same tomorrow? Don't be shy. Someone. Thanks. One person nodded their head. Perfect. We might not be, because someone might have updated the packages, right? So if we go look at this, it's not reproducible. Singularity could have changed, Docker can change, or the package repo that we pulled from could be different. So instead of getting version 131 of the package, we got 131-2. Now there's just slight differences that might impact our code. So what can we do about that? We can make a layering system. So what we can do is reach out to the internet once and only once, pull down this container, and then build off of that, making the next container point to that previous one, and then include our steps in our definition file. So the post section, for example, in this little example here, is just bash commands. So it's just saying, depending on the OS you pick, apt install or dnf install or yum install, right? Or other things you do, download source code, compile it, things like that, right? And so we can make those things be more reproducible and persistent if we do this in this way. So now we can keep doing this layer as many times as we want to. But since we're talking about HPC, we have to talk about the giant gorilla in the room, right? Which is MPI and InfiniBand or OmniPath or whatever low latency network that you're using, right? How do we handle that in this environment? And this is from the standpoint of Singularity right now. So there's two main methods for doing this. There's the bind method and the hybrid method. Now, for MPI, and thanks to, I think his name was Jeff from NVIDIA earlier, gave a great talk about the ABI interface. I used the word interface, but application binary interface for MPI and how that works. I thought that was great. Goes really well with this. So for the bind method, what we're going to be doing there is we're going to be taking the MPI that's installed on the host system. So for example, most of you familiar with modules, like you use a module load and you get your environment. So it would be taking that and binding it directly into the container itself, and that's what we're using to build against our code. So we use the systems version of MPI to build. The approach that we took is the hybrid method. And I should note that, as you guys can see there in the bold, in the bind method, there's limitations. There's benefits, you get speed, but there's limitations in that the host OS and the container OS have to be binarily compatible, right? So we can't use, for example, everyone here like Ubuntu? Everyone else use Rocky Linux or Red Hat? You can't have those two interrupt in this way. So bind method doesn't work for that. So some applications just work great in Ubuntu. It's easier because they have a lot more packages that are newer and you can get things installed quicker. But if you use that method, it doesn't work. So moving on to the hybrid method, what we do instead is we use containers MPI and containers InfiniBand. So we install MPI and InfiniBand into the container, and then we rely on that ABI compatibility to make those two pieces work. For the InfiniBand piece, we rely on the fact that they're series compatible. So if it's a 5.1 of OFED, then you need to have something that's series compatible with 5.1. We try to stick with long-term support versions, and I'll talk about that on the next slide. Sorry, getting ahead of myself. And then, like I mentioned in the hybrid method, you have system MPI and you have system InfiniBand. So again, those two talk through that ABI compatibility. So like Jeff's talked about, for example, in the container, if I install MPICH, that means I can use MVAPICH or Intel MPI or Cray MPI on outside the container. And if I install OpenMPI, I can use OpenMPI or HPCX, and I forgot the other one, IBM Spectrum, I think was the other MPI. So those ones will work together. But for example, I couldn't take, in my container, if I used MPICH as the MPI that I wanted to use for my application, and then on the outside I decided to module load OpenMPI, they wouldn't work. And what I mean by work is it would run, it just wouldn't give you valid results. It would fork off a process for each one that don't communicate correctly. So this is our strategy. It's a very simple strategy, and there's 3 key elements to it. The applications are built in layers, as you can see from our pyramid here. The key components, we group them into a single layer, and then part of that reproducibility that we were talking about, and portability and things like that, is we try to handle that by doing local mirrors. So I don't go out to the internet for anything. I store static copies of everything that I do when I go to build these environments. And then we also use some type of OCI registry, such as Harbor is one of the ones that we use for simple fingerprinting and making things a little easier and quicker when it comes to building these pieces. But what's important about this one is that the bottom layer is the thing that changes the least. And then as we work our way up the pyramid, it's the things that change more frequently. So if things work out great for us, we'll only be changing that top part of the pyramid over and over and over as we recompile these applications and don't really have to touch the other layers unless there's some big change. And then let's say I did have to change the interconnect layer, for example. Let's say a series compatibility issue came up and I needed to change that one. I'd only have to build from that layer up in the stack. I wouldn't have to build anything down below. So we do make some assumptions with this. We assume that whatever the host system is, they will hopefully use long-term support versions of the driver and software stacks. So that way it's more long-lived. You can get 5 to 7 years out of these layers compared to non-long-term support, which is usually like a 2-year cycle. And then on top of that, we assume that host system administrators would be willing to install some ABI-compatible MPI on the system if one doesn't exist. So again, like we just talked about, if you only are using MVAPICH, for example, in your container, and they don't have MPICH or MVAPICH or Intel installed on the host system, they'd be willing to install that instead of just saying, nope, you have to make OpenMPI work. So let's look at a basic container definition file. So this is the base layer of the pyramid. Again, some of you aren't familiar with this. So this is a pretty simple one. All I'm telling the system to do here is go out to Docker, grab the one called Rocky Linux that's version 8.6, and then we also store some information in the post section about the build system itself. That might be useful later on if we need to reproduce these results. So we know what type of architecture was built on, the kernel that was used, and then we test to make sure that the system comes back with what we expect. So my simple test here just tells me that Rocky Linux is the OS. And then we can put some info in there about who created this, what version is it, and users get a nice help message. Well, this one's kind of lame, but they can get a help message about the container. So next in the stack is the one that's for compilers, and this is the one that's, to me, is important because this is where we stop pointing at the internet for all of our packages and point to our local static mirrors. That's what that first section does. And then from there, we rebuild our caches and install necessary compilers, tools for editing files, and things like that. And then gather those same metrics again for how it was built and what system it was built on. Next in the stack is the Interconnect Drivers. So this one took me a little bit, and I'll talk about this a little later when it comes to the MVAPICH2 and Moose piece, is that we used to have it where this layer didn't play nicely when you installed both the InfiniBand drivers and the OPA drivers in the same container. It would cause some weird results to occur. And so it took a little while to get those two installed correctly together. So now instead of having forks in the tree when you go to build these pieces, we can do this all with one container all the way through. So this way users don't have to worry about if they're building against InfiniBand or building against OmniPath in this example of this layer, they can just do it with this one. And there's just some simple instructions in here to go grab them and install them in user space. And then finally, the second to last layer here is where we add the MPI into this. And so one of the benefits to this strategy is that if you don't need MPI, for example, you can just build your container against the an interconnect layer. And if you don't even need to use that and you just care about compiling some basic code, you can just build against the compile layer as well. And so in this one, all we're doing is keeping everything inside of that definition file. So you notice that we're creating a here document on the left for doing our hello world MPI. And the reason for this is that traceability. So again, this is software quality assurance. So from a paperwork standpoint, those kind of pieces, I might be asked what went into this, and I need to track these kind of pieces. And this is where the definition file is good for that. So as long as I have the container, I can tell it to show the definition file used to build that object. So let's move on to some of the stuff we did for testing. We had 4 different systems that we tested on, and there's 2 caveats here, or 2 little footnotes, I guess, the 1 and the 2. The 1 was the systems we used for portability testing. So we built, using that pyramid that you saw on the last slide, we built 3 different applications. And Lulish, we used the OSU benchmarks, and then MCMP. And so for a portability standpoint, we tested on these 4 different systems. You can see that they're different architectures. 2 of them are Intel-based, AMD, And then the Galena one is also Intel-based. They have different interconnect fabrics, EDR, HDR, different drivers, 4 series, 5 series, non-LTS series, OmniPath in one of them, and then 3 different operating systems. I should say flavors of operating systems, CentOS 7, and then Rocky Linux 8, and then Ubuntu. So, and then the first 3 systems, Sawtooth, LMH, and Hoodoo, they were the ones that we actually used for performance metrics. As you see, Sawtooth's about 100,000 cores, and LMH's 20,000 cores, and then Hoodoo's 352. Now, Hoodoo is our AI/ML cluster, which is why it doesn't have a lot of cores, but it's got a lot of GPUs for training our ML models. So let's look at some results here. So Lulish was run for 1,000 iterations with 30 to the third points per domain. And in our container, we installed both MPICH and OpenMPI. And again, the reason why we did that is to cover the broadest amount of MPIs that our users typically utilize. And so we have 2 different executables built when we built this application layer in the same container. So we have one built against OpenMPI 414 and one built against MPICH 343. And at each core count, the simulation was run 5 times, and the average run is reported here. So we can see that the container for OpenMPI is a little slower than the native performance on Sawtooth. And we got some slightly weird results for the smaller core counts, but you can see at higher core counts, between 4,000 and 8,000, they're very similar in performance. So now let's look at LMH and Hoodoo here. So on LMH, we just used OpenMPI 411 and got very similar results between the container and the native performance. And then on LMH, we saw a little bit underperformance at the higher core count for the container, but we saw a little bit better performance at the lower container, or the lower core count of 64 cores. Let's move on to the OSU MPI all-to-all. This is version 7 on 10 nodes. And we got really good scaling here for the container. Someone was asking me earlier, do containers typically slow down or speed up the performance of applications? And there's quite a few other papers that have done very good studies with this, showing that containers can either perform as well or better in some cases than native applications. And so we can actually see that here on this on our runs for using MVAPICH, for example, a 235. We got better latency using the container versus native, which was a very interesting result. And then looking at LMH and Hoodoo again, we see that the container and the native performance are on par with each other as we go through this. And finally, let's move on to the MCMP container. This one's a little embarrassing for us because as we look at this graph, so native's faster the higher up it is in the graph, and the container's faster the lower it is in the graph. So let me ask, can anyone tell me what this shows us, what mistake we might have made? That's okay if you don't. So what this shows is that we just didn't optimize our native install on the system very well, since the container is getting such better performance. So we went back and we reinstalled the application natively, and the results were much better. The container was still slightly faster in some cases, but we didn't see this 5x loss in performance in some places. So coming to MUG, I have to have something that involves MVAPICH, right? And one of the ways that we can incorporate this is that we work closely with the Moose team. And one of the things we saw is that, and this is one of the graphs I borrowed from Matt Anderson's talk last year, is that during the January 2021 to September 2021 period, there wasn't a lot of loads for the MVAPICH module compared to OpenMPI on our systems, as well as Intel MPI. But on this new updated graph with metrics, we see that the MPI usage has drastically increased since January 2021 for MVAPICH. And this is because of the Moose framework. So the Moose framework is a multi-physics object-oriented simulation environment. That's what Moose stands for. And it's the basis for nuclear modeling and simulation tools developed at INL. And so at first when I saw these metrics, I didn't really understand why we were seeing such a drastic increase, but MVAPICH is the preferred MPI tool for Moose, and they do lots of builds with their CI/CD pipeline. So we talked to them about our strategy for containers. The Moose team was just getting started with containers, and they decided to incorporate it into their CI/CD system. And in doing so, because they were forking off so many different applications. So Moose is kind of the base for a lot of different applications. It's called the herd apps. They have Griffin, Bison, Marmot, and lots of others. They use the MPI plus base plus container for their continuous integration. And this reduced a lot of their builds from hundreds a week down to 20. And so now they can take these simple applications that they build once and run it on all of our systems. And so it simplified their build process drastically, and now they're able to go back and grab, due to the fingerprinting in containers, they can verify the results of their builds and go back and find them and rebuild them again if they need to, and get the same results. And like I mentioned, it runs on Sawtooth, LMH High, and Hoodoo without any issues. So to me, this is a very interesting result. And this is one of their container definition files over here where they actually do a lot of Jinja templating themselves. This is before Apptainer 2.0 that has templating as well built in. So it really, again, improved their CI/CD workflow. So to wrap this up, I rambled a little too much. I apologize about that. The strategy shows that we have portability across supercomputing architectures. We have reproducibility due to layers and local mirrors. We have traceability because those definition files get baked into that image that's immutable. And then we simplified this because now HPC staff only has to focus on MPI ABI compatibility and then driver series compatibility. And finally, it secures the user against security updates on the system. And that's all I got for you.
Thanks a lot. Any questions?
I was okay with no questions too, since I did such a good job, right?
Okay. So yeah, thank you, Matthew, for the great presentation. So you've shown Moose as like one application that can really benefit from containers because it's very complicated to build. How easy would it be to do the same for like other applications, like deep learning applications, and which also consist of many layers and
Great question. So deep learning frameworks are a little more challenging because they rely on the NVIDIA driver series, right? And so NVIDIA's actually got a lot of their own containers that they put out there. They're Docker containers. If I remember right, it's called the NVIDIA NGC. Yeah, cloud. It's their cloud container. It's their own hub of pieces like that. So what's good about that is that you can build off of those if you want to, or you can end up doing it yourself using some kind of layering strategy like this. And the reason why I bring that up is they mentioned the types of drivers that are compatible themselves. So there's like the 460 series, the 470 series. You skip the 480s, you can go to 510, 520. And so as long as you keep that driver stack installed in your layer, then you'll be able to run it on lots of different types of hardware. And so it's possible to do, it's just a little more challenging because there's restrictions on the driver series. So you'd have to work a little closer with your system administration team to say, hey, this is what's installed in the container. And as long as they're willing to move the drivers they have on the system to be one of the ones that are compatible with that, it would work just fine. Welcome.
Yeah, I would like to ask two questions, actually. Hello?
I was going to say,
yeah,
I couldn't hear you, so yeah, ask away. I've got.
Yeah, one is, do you have a good explanation why containers perform better than your raw system? That's one. Second, with the container, let's see in your distributed system, when you test it on different scales, does the characteristics showing something different on that? With the same container you built?
Okay, so I'll ask you the first one, and I need you to repeat the second one for me. So the first one's simple. I really don't know why it performs faster. Some of the other papers I read weren't really sure either. Now the performance when it's better in some regards, so I can answer that two ways. First one is, let's say we did everything perfect on the system and built the perfect application and optimized it the best way possible. And some of the other papers, when they did that, when the container performed better, it was like 0.1% or 0.2% faster. So there's just this small uptick in performance.
Consistent, right?
It was for their results.
Consistent and reproducible.
Correct.
Yeah. So there must be a reason behind it.
I agree. I just haven't had enough time to investigate.
Let me explain the reason for the better performance of the container. First of all, when you build a container, you don't include the libraries, which are like we as a system administrators install on the systems to track your usage or to track multiple things. You don't have those libraries in your containers, and that's why they perform faster. And the other reason could be when you build a container, you might be using the latest libraries, suppose latest application binaries or latest MPI or latest Ubuntu or that kind of systems which have already done those optimizations, and your system might be couple of versions behind. So these two reasons I feel, and I have seen this in my experiences, like when container was showing better performance, better latency than the
And
underlying
that makes
system.
a lot of sense.
Yeah,
I
that
can
makes
understand
sense.
that. Yep.
So yeah, avoiding those libraries that track and the latest version can give you better performance.
And the second part to that is we just didn't do a very good job optimizing it for our system. So that's why in our results, we had some that had such weird skewed results. It's because we realized that what we thought we optimized well, we just did not. And that was part of the bigger reason there.
So what's the largest scale has you tested?
Say that again for me.
What's the largest number of ranks have you tested your containers?
I think we went up to 12,000 or so, somewhere around
And
there,
all
or
of them
20,000 cores.
Okay, so what I mean is the same container image can scale with this consistent performance characteristics.
Correct. That's
Okay.
what we saw in our performance.
I ran my containers up to almost like 400,000 container instances, like 8,000 nodes on Frontera system, and they did pretty well. So
Right.
they scale, and we had a paper in ISC 2021 showing these performance numbers.
Right.
Thank you.
Welcome.
So 2 questions. One from me. You said all those numbers were taken with Singularity, right?
I'm a little hard of hearing. Say it again for me.
All the numbers you said they were taken with Singularity, right?
Correct.
Was there a specific reason? Does it run faster? Is it
Oh,
easier to
nope.
build?
Nope, just what we were using at the time.
Okay. And then we had a question from the chat from Adam Moody. Great talk. I like your approach of using layered containers. Regarding long-term reproducibility, is there a policy for users to capture and or specify external software like job launchers? For example, the Slurm version for expected SRun behavior.
Great question. That's what we're designing right now. We're trying to come up with everything we can think of to help make this more reproducible 5 years from now and capture all the metrics that we can about it. And we don't want to obviously capture too many because we don't want a bunch of metadata sitting around that would convolute it, right? So we're in the process of defining what that policy is for users. And so we've given some hints about what they should capture when they build it, and then maybe make a README that goes along with it for way they're submitting it to the system, so we know more about that. And to get a little more clarification, the reason why we picked Singularity, I should have said this, and Apptainer is because they create a CIF file. And so we didn't want to have to deal with having to write containers to a local non-FS file system.
Okay. Thanks.
If that makes sense.
No, it makes sense. Yeah. Thank you.
You're welcome. So let's give the final. Thank you.
So we'll move to the